Hi, my name is Andreas Mountakis. I am a postdoc at the University of Crete, and together with my collaborator Dimitrios Charamaras, we wrote a paper entitled Finding Product Sets in Some Classes of Amenable Groups. The paper got published in Forum of Mathematics Sigma. This video serves as an introduction to the paper. Let us start with some motivation. So in 2022, Moreira, Richter and Robertson established the following sumset conjecture of Erdős. They proved that if a set A of natural numbers has positive upper Banach density, then there is some natural number t and an infinite sequence of natural numbers, so that the sumset t plus b, where we exclude the diagonal, is contained in A. Here we should say that the result of Moreira, Richter and Robertson is in fact a two-step density analog of Heinemann's theorem on IP sets. Now it is natural to ask if an analogous result holds in other countable groups or semigroups. For example, can we prove an analogous result for abelian groups or more general groups or semigroups? Now, for this question to make sense, one shall consider groups where there is some notion of density for sets. That's why we write here one shall consider semigroups or groups in which a notion of largeness can be defined. Now those groups are well studied and they are the so-called amenable groups. Let us define what it means for a group to be amenable. Given a countable group, a sequence of finite subsets of G is called the left-Follner sequence if it is asymptotically invariant by translation from the left. And we give the definition here. We want this limit to be equal to 1 for all G in G. Now, G is called amenable if there is some left-Follner sequence in G. And for a set A subset of G, we say that A has positive left upper Banach density if there exists some left-Follner sequence which gives it positive upper density. And this is the definition, this lim sup here is the definition of upper density of a set A with respect to some Follner sequence Phi. Now the question, after introducing amenable groups, is under what assumptions can we prove a theorem analogous to the theorem of Moreira, Richter and Robertson for amenable groups? Namely, under what assumptions on the group G can we guarantee that every subset of G with positive left upper Banach density contains an infinite product set? In this paper, we address this question and we extend the theorem of Moreira, Richter and Robertson to all amenable groups which have the property that the set of squares has a certain largeness property which we call square absolute continuity. Now here we do not give the definition of square absolute continuity because it is somewhat technical, but one should think of it as the set of squares in some sense having a positive density in the group. So now we're ready to state our main theorem. Our main theorem says that given an amenable group that is square absolutely continuous and a set A in G which has positive left upper Banach density, there always exists an infinite sequence Bn and some element T in the group, so that the product set T times Bn times Bm, where n is smaller than m, is contained in A. Furthermore, we prove that all finitely generated nilpotent groups are square absolutely continuous, and also all abelian groups for which the subgroup 2G has finite index in G also are square absolutely continuous. Now observe here that for abelian groups, instead of G squared, we write 2G, and the reason is we think of abelian groups with additive notation. Note that examples of abelian groups where 2G has finite index in G include finitely generated abelian groups and groups of the form Fp to the omega, i.e. infinite direct sums of the group Fp with itself, where P is any odd prime. Let us now state the special case of our theorem for abelian groups. For abelian groups, the theorem reads as follows. Given an abelian group where 2G has finite index in G and a set A in G which has positive upper Banach density, we can always guarantee the existence of an infinite sequence Bn and some T in G, so that T plus Bn plus Bm where n is different than m is smaller than a. Now here one should observe that for general amenable groups, our theorem has the following form. We ask here that t times bn times bm, where n is smaller than m, is contained in A. Now for abelian groups, our theorem would give here n smaller than m, but since the group is abelian, we can interchange the role of n and m by just using commutativity, so we get this result, which is a bit stronger, but in fact it is equivalent. Our results provide answers to several questions and conjectures posed by Cram, Moreira, Richter, and Robertson in a recent survey. We should also note here that Theorem 2 is optimal, as was shown in a recent preprint by Ethan Eichelspberg. Eichelspberg showed that if 2G has infinite index, then we can always find the set A in G which has upper Banach density arbitrarily close to 1, which fails to satisfy the conclusion of Theorem 2. Eichelspberg's example also shows that Theorem 1 cannot hold without any condition on the amenable group. So some condition like the one we pose for the squares d squared is necessary. Let us now say a couple of things about the proof ideas involved in the paper. To prove our theorem, we use ergodic theoretic methods inspired by the work of Cram, Moreira, Richter, and Robertson. We use Furstenberg's correspondence principle to translate the problem into a dynamical statement. Then our goal is, given an amenable group and an ergodic measure preserving action of G, we want to find certain configurations which are called Erdős progressions, and they are obtained by limit points of orbits. We should say here that those progressions, the Erdős progressions, were introduced by Cram, Moreira, Richter, and Robertson in their work where they proved Erdős conjecture. It turns out that the natural environment in which one can study the Erdős progressions in a system is the Kronecker factor of the system, because in the Kronecker factor of the system, the Erdős progressions are simply the three-term arithmetic progressions, which are easy to find. It's an easily tractable object. Finally, we have to define appropriate measures so as to lift an Erdős progression from the Kronecker factor to the original system. I will not mention anything more about the proof ideas. I think these are some central points in our proof. I hope you found this short presentation interesting, and I encourage you to look into the paper. Thank you.